Kargo Autonomous Delivery Vehicle is a fully electric, self-driving delivery system developed by Academy of Robotics, designed to revolutionize last-mile logistics. It aims to reduce up to 90% of the cost and emissions associated with traditional delivery vans by autonomously navigating residential, suburban, and urban streets without a human driver. Kargo is powered by a sophisticated artificial intelligence system that integrates high-resolution cameras, ultrasonic and infrared sensors, and GPS to perceive its environment and plan safe routes. Unlike many autonomous platforms that rely on costly sensor arrays, Kargo emphasizes advanced vision-based machine learning and proprietary terrain training software to detect obstacles, pedestrians, vehicles, cyclists, and road features in real time. The vehicle can reach speeds of up to 60 miles per hour and complete typical delivery routes of approximately 60 miles on a single charge, offering zero-emission operation for daily logistics. Its modular internal package sorting system holds dozens of small parcels in dedicated compartments and automatically presents the correct item at each stop. Customers receive real-time notifications as Kargo approaches and access their delivery through a secure verification process. Festo BionicSwift redefines engineered flight with lifelike precision inspired by swallows. Developed by Festo's Bionic Learning Network, this robotic bird weighs 1.5 ounces and measures about 17.5 inches long, with a wingspan of 26.7 inches, making it incredibly lightweight, yet capable of complex aerial maneuvers. Its wings feature flexible, ultralight foam lamellae layered like real feathers and connected to carbon quills, allowing the bird to fan open on the upstroke for efficient airflow and close on the downstroke for powerful lift. This feather-inspired design boosts flight efficiency and agility far beyond traditional flapping wing machines. The body houses a brushless electric motor, precision servo motors, a battery, and compact control electronics that adjust wing beat frequency and tail movement to perform loops, sharp turns, and smooth flight. Navigation relies on a radio-based indoor GPS system using ultra-wideband technology, which tracks position via anchors and a central controller. This enables individual birds or coordinated flocks to follow precise flight paths even in confined spaces. Flight time reaches about 7 minutes per charge, and the system allows safe autonomous flight in tight environments. The BionicSwift combines natural wing mechanics, real-time localization, and compact flight systems to bring bird-like agility to robotics research and advanced aerial applications. The Highwonder Jet Arm is a high-performance, 3D vision robotic arm designed for advanced ROS education and AI development. Powered by Jetson Nano, Orin Nano, or Orin NX as its main controller. It works seamlessly with both ROS 1 and ROS 2, making it a flexible platform for robotics students, researchers, and builders pushing into real-world automation. The arm uses 6 intelligent serial bus servos that deliver 35 kilograms of torque, giving it the strength and precision needed for accurate manipulation tasks. A built-in 3D depth camera pairs with a 6-microphone array and multimodal AI large models, enabling the robot to perform tasks like 3D spatial grabbing, object sorting, target tracking, scene understanding, and voice-controlled operation. Its RGB plus depth fusion detection system allows the jet arm to perceive objects in full 3-dimensional context. By combining color data, coordinates, and depth mapping, the arm identifies object position, orientation, height, and distance, allowing it to execute precise grabs and movements in complex environments rather than relying on flat, 2-dimensional cues. With its balanced mix of power, vision intelligence, and developer-friendly tools, JetArm stands out as a capable educational and research robot arm for hands-on robotics, machine learning, and perception-driven automation. Exomotion is a next-generation robotic exoskeleton created by Human in Motion Robotics, an SFU spin-off built on 10 years of research aimed at restoring real mobility for people with lower limb paralysis or severe walking impairments. Unlike earlier systems that demanded crutches or walkers for support, Exomotion can stand, walk, and balance entirely on its own, allowing users to move independently without external aids. Its defining feature is a self-balancing control system that mirrors human biomechanics. Embedded sensors read the user's weight shifts, posture, surrounding terrain, and movement intentions, then generate fully balanced natural motion in real time. The exoskeleton does not simply lift and move the legs, it actively stabilizes the user's whole body while walking, sidestepping, climbing stairs, crouching, and adapting to uneven ground. Development began in 2014 under SFU researchers Siamak Arzampor and Edward Park, whose goal was to eliminate the dependence on crutches that limited earlier exoskeleton designs. Human in Motion Robotics now develops Exomotion in two parallel versions. The U-Hawk robot helicopter transforms the legendary UH-60L Blackhawk into a fully autonomous, crewless aerial workhorse. Developed by Sikorsky in collaboration with Lockheed Martin, this variant removes the cockpit entirely, converting the space into mission volume and increasing internal cargo capacity by roughly 25% over a standard Blackhawk. A third-generation fly-by-wire system paired with the Matrix Autonomy Suite allows operators to task, launch, and recover the helicopter from a single tablet. The system autonomously plans flight paths, avoids obstacles, and manages takeoff and landing, enabling operations without a human pilot on board. The U-Hawk can self-deploy over distances up to 1,600 nautical miles and loiter for about 14 hours without refueling, supporting long-range logistics, resupply, and persistent missions in contested or remote areas. Payload capabilities include approximately 7,000 pounds internally, 9,000 pounds on an external hook, and combined loads of up to 10,000 pounds. Tiny 3D printed cars have become a proving ground for what rapid manufacturing can do at the smallest scale, turning digital designs into miniature vehicles with working wheels, suspension elements, and even compact motorized drivetrains. Hobbyists have pushed this to impressive levels, creating micro car kits built from lightweight components that snap together without adhesives. Builders simply trim away supports, smooth the axles and housings with light sanding, and use pencil graphite as a dry lubricant, allowing the wheels to spin freely once assembled. More advanced communities have developed complete model libraries that include print files, assembly guides, and sourcing lists for the non-printable parts such as motors, magnets, and tiny electronics. These builds rely entirely on screws rather than glue, so if a component cracks, the owner can print a new one and swap it in within minutes. Computational lithography is the collection of mathematical models and algorithmic techniques used to push the limits of photolithography, the process that imprints circuit designs onto silicon wafers. It became essential in 2008 when the semiconductor industry began shifting toward the 22-nanometer CMOS process, a point where traditional optics could no longer produce clean, accurate patterns on their own. Every advanced processor and memory chip manufactured today depends on these methods. The core idea is straightforward in concept, but extreme in execution. Light passing through a photomask does not behave perfectly. It diffracts, bends, blurs, and distorts features to the point where the patterns reaching the wafer no longer match the intended chip design. At the nanometer scale, even tiny distortions would render a chip unusable. Computational lithography solves this by predicting those distortions in advance and modifying the mask so that the printed result comes out correctly. Building these corrections requires a deep fusion of electromagnetic physics, photochemistry, computational geometry, and massive distributed computing. Each modern photomask demands iterative optimization loops that simulate how light interacts with three-dimensional mask structures, how materials respond chemically, and how focus and exposure vary across the wafer. For a cutting-edge integrated circuit, generating optical proximity corrections alone can consume roughly 100 CPU years of computational effort. Pivotal Helix is a personal all-electric vertical takeoff and landing aircraft designed for everyday flight, combining aerodynamics, lightweight materials, and electric propulsion to make flying simple, safe, and accessible. Weighing just 348 pounds and constructed primarily from carbon fiber composite, the Helix is classified as an ultralight vehicle under FAA Part 103, meaning it can be flown in uncontrolled airspace without requiring a pilot's license. The aircraft features joystick controls, a user-tested integrated flight panel for instruments and navigation, and a forward-hinging canopy, providing a wide 270-degree view for pilots. The entire aircraft tilts for vertical takeoff and landing, rather than using rotating wings or rotors to reorient thrust, reducing potential points of failure. 8 lightweight electric motors, each weighing 4 pounds but producing 130 pounds of thrust, power the 8 fixed rotors mounted on tandem wings. Flight is controlled by independently varying rotor speeds, similar to consumer drone technology. An 8 kilowatt-hour battery pack, divided into 8 modules, powers the aircraft, with proprietary chemistry ensuring the cells can deliver 100% of rated discharge down to 20% remaining capacity. This provides more than a 20-mile range with a 20% battery reserve, though real-world range under ideal conditions is approximately 17 miles. Cruising at 63 miles per hour, the Helix climbs and descends at rates up to 500 feet per minute. GoPro Max 2 is GoPro's newest full 360-degree action camera, introduced in September 2025 at a price of $500. It represents a complete rebuild of the company's spherical imaging system, packing higher resolution, stronger color science, and field-ready durability. The camera records true 8K 360-degree video at 30 frames per second, with 10-bit color depth and GP-log encoding, which supports more than 1 billion color values for professional-grade workflows. With GP Labs firmware installed, the Max 2 can reach byte rates up to 300 megabits per second, delivering the highest data rate available in any consumer 360 camera and giving editors significantly more detail to work with during post-production. For high-motion capture, the camera records 5.6K spherical footage at 60 frames per second for smooth, slow-motion playback. It also records 4K at 100 frames per second for 3 times slow motion. When used as a single-lens point-of-view camera, the Max 2 delivers 4K video at 60 frames per second with the Max Hyperview digital lens, producing an ultra-wide 180-degree field of view. Terran R is a partially reusable, 3D printed orbital launch vehicle under development by Relativity Space, with its first flight expected in 2026. Standing between 270 and 284 feet tall, with an 18-foot diameter and a 16.4-foot payload fairing, Terran R represents a major evolution from the company's smaller Terran 1 rocket. The vehicle is designed to deliver 51,800 pounds to low Earth orbit with a fully reusable first stage, and 73,900 pounds to low Earth orbit if fully expended. For comparison, this payload capacity exceeds that of SpaceX's Falcon 9. The first stage uses 13 Aeon R engines, producing an estimated total thrust of 3,350,000 pounds. The Aeon R first stage engine went from design to qualification in just 14 months, showcasing the speed advantages of Relativity's manufacturing approach. The second stage uses an upgraded Aeon R vac engine and will be expended along with the fairings. Terran R is built using advanced metal 3D printing, though the production approach has evolved. Initial versions use aluminum alloy tank straight section barrels in a hybrid manufacturing approach, combining 3D printed components with traditionally manufactured sections to meet rapid launch timelines while balancing innovation with production speed. M1-wheeled Quadruped robot is being hailed as the world's first true-wheeled quadruped, a robot that blends the agility of four-legged movement with the speed and efficiency of wheels to create a new class of mobile robotics. Its hybrid wheel and leg design lets it cruise quickly across smooth surfaces while maintaining the ability to step over obstacles, climb stairs and handle rough, uneven terrain with graceful transitions between rolling and walking motion. This dual-mode mobility comes from an innovative parallel joint drive system that not only improves force efficiency but also enables seamless shifts between high-speed wheeled travel and adaptive legged navigation across challenging ground. M1 leverages real-time perception and motion control algorithms to evaluate terrain on the fly, autonomously choosing the best locomotion strategy without human input. Skydagger Fiber Optic System is a high-security communication solution for tactical drones that replaces traditional radio links with a physical fiber optic channel running between the drone and its operator. Unlike wireless control, this tethered optical link is immune to radio frequency interference, jamming, and signal blockage, giving operators a rock-solid connection even in contested environments where electromagnetic interference can knock out conventional control systems. Fiber optic communication also delivers high bandwidth and low latency, enabling real-time transmission of control signals, telemetry, and high-definition video from the aircraft back to the ground. The system is offered in multiple range options with fiber lengths supporting 3 km, 5 km, and 10 km deployments, letting mission planners select the right balance of reach and weight for each operation.